Assalamualaikum and good day everyone. Okay, so now is 26 April 2021 and the time is 1:32 a.m. Okay. Okay, just to take note to you guys the timing, so maybe my voice need to be low because everyone is sleeping, and also maybe there will be some distorted focus, or maybe I will be having some typos, okay, due to late night, okay, but inshallah I will try my best, and don't worry. So okay, I'm also mentioning the time is not because for me to show that my effort in doing the job late night for you guys, but it's just to show EMT is a two-way effort, okay. So the lecturer need to put some effort and the student also need to put some effort. So hopefully you guys can make through this subject, okay, and of course the effort is more towards the students, okay, because you the one that will sit for the test, you're going to have to do the exercise in order for you to familiarize with EMT, how to solve it, okay. By now you should know that EMT is challenging subject because from the syllabus you can see it is interrelated. The current topic will be heavily dependent on the previous topic, okay. So please try exercise and everything, okay. I really hope that you only need to go through this subject once, okay. No need to repeat this subject, okay. So try your best, inshallah, and like other lecturers, I want to see all of you guys pass this subject or even to get A, okay. Okay, now without further ado, we are going to cover week 6, okay, from the course informations. Okay, week 6 is about Laplace and Poisson equation, okay. I may be pronounce this wrongly, okay, but because I was in France for works last time, the way to pronounce this letter is actually Poisson, okay, but I don't know the real pronunciation. However, this is not important. We are not going for any English test, okay. So what we expect for Laplace and Poisson equation is to introduce us to the uniqueness theorem, okay. Uniqueness theorem, the solution of electrostatic problem, okay, electrostatic problem with Laplace and Poisson equations, okay. So what have been okay, while I'm teaching, you guys will hear clicking sound here and there, okay, because I'm trying to refer to the slide, I'm trying to refer to the course information, I'm trying to refer to the book, okay, the physical book beside me, and I'm trying to refer to some other information in order for me to try my best to teach you guys, okay. So please bear with me, and hopefully you guys can watch this video until the end. And before that, as always, please watch the supplementary videos or the link that I've shared, okay, from the retired professor. It's really helpful. He covered a lot, okay. It's depend on your effort to watch all the videos, okay, to watch all the video and to try the exercise, okay, because we cannot cover all in class, okay. Because if I were to cover everything, then we will be out of track, okay. Then we have a lot of additional class needed. This one is mine, not considering that there is holiday, meeting, or some other else in that might disturbing our schedule, okay. Okay, so what have been studied so far before the uniqueness theorem, okay. What we have been studied, okay, uniqueness theorem, we will start from the uniqueness theorem. We will study about Laplace and Poisson to solve electrostatic problem. But before this, okay, what we have been studied so far, okay, in the model, in the previous, like Coulomb's law and everything, trying to solve what we want to solve, the, okay, rho v, electric field intensity, our D, our Q, okay, sorry, Q, our WE, our V, our sigma, our epsilon, our resistance, our capacitance, okay, and a lot others that we try to cover. This one is actually analytical model, and you see it is a bit more complicated, okay, more complicated. And if you miss some important information, or you might miss the way of integrating, you write something wrongly, then the whole process burn already. Okay, so the next is what been told by the graphical methods. Okay, graphical methods. So the uniqueness theorem. Okay, so the uniqueness theorem, however, depends on regional condition, and second is our boundary condition. Okay, uniqueness theorem depends on this, means the solution to an electrostatic problem is unique if it's obey these two conditions. Okay, so before I proceed, okay, it's equal. Okay, you may refer this subject, this topic, from page 2 to 6. Okay, there's no number of pages, 2 to 6, 2 to 6, 2 to 7, until the end. Okay, you may try the exercise. Okay, you see the detail, how to do the practice. Okay, okay. So what is actually in the solution to an electrostatic problem is unique when it's obey this condition, right? So what is actually regional conditions? Okay, when we have a boundary, for example, if we have a boundary, okay, let's say spherical, okay, then this inside here is the regional, okay, regional condition, whatever is happening inside. Okay, regional condition. For example, what is the best way to represent this? Okay, that what charge density to represent all sorts of other charge density type is rho v. Okay, because inside rho v you have rho s and rho l, so you have rho v here. And the next is the boundary condition. Okay, depends on the boundary, your boundary condition. Okay, here you might use the boundary condition that you already learned in the previous week 5, which is the electrostatic field in medium. Okay, so electrostatic medium week 5 is a very wide topics. It actually take more than 1 week to finish. Okay, however, luckily we have videos that cover all of this. It's not that I totally depends on the video, but it's the fact that the videos is already there online. It's just for you to watch it. Okay, so okay, without further ado, we will proceed. Okay, we will proceed with this condition. Okay, so if there is if you want to solve, okay, to solve for v, we can have the region based, we can solve it regionally based on the information that we can have, like rho v. Okay, so you may refer to the slide as well. Okay, I sometimes will refer to the slide, and sometimes I will refer to the book. Okay, but this lecture video is actually a combination of everything. Okay, combination of everything. So I doing summarizations. Okay. Okay, what we have learned from our Maxwell equation. Okay, remember how many Maxwell equation that we have learned? You guys need to know. First Maxwell equation is what? Second Maxwell equation is what? Okay, this one should be in your mind already. Okay, inshallah. But if not, you just recall on the page of the definitions, like Coulomb's law, Gauss law, and everything. Okay, they will include Maxwell. Don't skip in reading, because you might miss important informations. Okay, so we recall the Maxwell equation, the first Maxwell equation. What is that? in point form, which is the divergence, okay? Divergence dot of our electric flux density is equals to our rho v, okay? Then from the D, here we know that it's actually D equals to epsilon E, okay? This one is depend, if it's in free space you can use epsilon naught, okay? Then you substitute it inside here. Remember, this one must be constant, okay? This one must be constant, otherwise otherwise it is not valid, okay? So never mind, I will proceed further before explaining, okay? So we include this inside, okay? Okay, rho v, okay? You can only take this one out, okay? Only if it's homogeneous or isotropic. What does it mean by this? Is that the distributions, for example, is even for all area inside that regional, inside that boundary, okay? So that's why, if let's say if you, for example, if your epsilon is in function of r, for example, okay, means at any value of the radius, the value of the epsilon is changes. So this one, if this is happen, so this is not valid, okay? You need to have a constant, means it's like a number only, okay? So when it is a constant, you can take it out. Then you have rho v, okay? Then from there, rearrange, you have rho v over epsilon, okay? Now, from this, you also get to know that E, okay? You also get to know from page 226, the E is this. E is equals to potential grad, okay, of V, okay? We have covered this potential gradient in the previous chapters, okay? If you don't understand, just feel free to watch my lecture video or my slide or even the book, okay? Or any other sources that can help you, okay? This is a potential gradient, okay? Equation for potential gradient. So as we can see that it gives the E equals to negative divergence of V, okay? So putting this inside, okay, then you will get what? What do you get? If you try to substitute this inside here, you will get divergence of V equals to rho V over E, okay? And there is negative, of course, here. So negative, you can put that side, okay? So you have, now you have square of del operator, okay? Equals to rho V over epsilon, and negative you put there, okay? So we have new name for this, okay? We have new name for this, which this one we call as Laplacian operator, okay? So if you okay, here, okay, after that we have the equations, okay? We have several conditions that we can change this value and we will obtain a Poisson equation, or we can have a Laplace equations, okay? So if your epsilon naught, if you have divergence square V equals to negative rho V over E over epsilon, so this one is your Poisson equation, okay? But if in the event okay, where there is rho v equals to 0, okay, means there is no volume charge here, okay, for a charge-free region. So this equation will become, okay, so this, what is the name for this now? It is a Laplace equation, yeah, okay. So you have two names, Poisson and Laplace, okay. And you may refer to equations 6.6 to 6.8, okay. This one you can see from Sadiko books 227. You can see there is different Laplace operator. Laplacian operator. So this one is for if the solution is involving Cartesian coordinates. This one is if involving cylindrical coordinate. This one is involving spherical coordinates. Okay, if this is covered in your list of formula, you don't have to memorize. Okay, we engineers, we normally just use. Okay, if ridiculous thing lengthy about this, maybe it's already inside the formula. I think yes. Okay, so okay, now we can see, you can read this page of this book yourself, okay, or someone who didn't have the book, okay. Okay, I can just you can freeze the video to read, okay, it's okay. Page 228, okay. Okay, now the next, okay, so this is the uniqueness theorem. If a solution to Laplace equation can be found that satisfies the boundary the condition, then the solution is unique. Okay. Okay, let me explain. So the theorem is proved by contradiction. We assume there are two solutions of V1 and V2, okay? Both of which satisfy the prescribed boundary condition. Let's say we have Laplacian operator of V1 is 0, Laplacian operator of V2 is equal to 0. What happens if this is 0? This is actually what? Laplace equation, right? So means V1 and V2 is the same at the boundary. So we consider their difference, which is Vd equals to V2 minus V1. Okay, this will obey Laplacian operator of Vd equals to V2 minus V1 equals to 0. So V difference, okay, difference on the boundary is equals to 0. Okay, so here from the divergence theorem, okay, so if you don't understand, please read about the divergence theorem. Okay, it have been covered in previous lecture, or even in the book you can find where is the divergence theorem. I try to find for you. Okay. Okay, so the divergence theorem is here. Okay, sorry, at the page 77. Okay, if you want to know more about divergence theorem. Sorry. Okay, so the from the divergence theorem, we know that divergence of A dv, okay, volume integral, is equal to closed integral of the vector A of the surface, closed surface, where S is the surface surrounding volume V and is the boundary of the original problem. Yes, and we let A equals to Vd, we use a vector of this. Okay, so this is a bit lengthy. Then since the integrand is everywhere positive, okay, so you have Vd equals to 0, and Vd is Vd is equals to V2 minus V1, constant everywhere in the V. Okay, now but equation 6.15 must be consistent with equation 6.9b. Okay, equation 6.95 here. Okay, must be consistent with equation 6.9b. Okay, here they must be consistent, means they must be satisfy the boundary conditions. Okay, hence Vd equals to 0 or V1 equals to V2 everywhere in the region. Okay, showing that V1 and V2 cannot be different solution of the same problem. This is the uniqueness theorem. Okay, just what I referred just now, that satisfy the boundary condition. So similar step can be taken to show that the theorem applied to Poisson equation. What is the Poisson? Poisson equation is just the same equation. It's just that instead of having 0, we have negative rho v over epsilon. Okay. And to prove the theorem for the case where the electric field potential gradient, potential grad, okay, this one is specified on the boundary. Okay, before we begin to solve boundary value problem, we should bear in mind the three things that uniquely describe a problem. Okay, the appropriate differential equation, whether we want to use a Laplace or Poisson. Okay, we need to really see the situation. If it's a rho v 0, then you use a Laplace. If it's a rho v having a value, so it is should be Poisson. Okay, now and then the solution region, yes, just like just now, the regional solutions, the regional condition, and also the boundary condition. So 2 and 3. Okay, now general procedure for solving Poisson or Laplace equations. Okay, the following general procedure may be taken in solving given boundary value problem BVP involving Poisson or Laplace equation. So solve Laplace if rho v equals to 0, just now, or Poisson if rho v is not 0, means rho v having value, using either A, direct integration, where v is a function of one variable only. Okay, this is very important. Of one variable only. Okay, so as you see from this book, okay, this is essential of electromagnetics, Southeast Asians. Okay, so it has been tailored to suit the Southeast Asian. Okay, so if you can see, so we follow the syllabus. Okay, so a direct integration when v is function of one variable only. For example, okay, let's say in the sphere, in the cylindrical coordinates, you have what? Okay, let's say in spherical coordinate, what variable you can have? You can have r, you can have phi, you can have z. Am I correct? How about spherical coordinate? You can have r, you can have theta, you can have phi. How about Cartesian coordinate? You can have x, you can have y, you can have z. Okay. So what does it mean by this is that, okay, v is a function of one variable. Okay, means that we will take the dominant one, the dominant change. Okay, the dominant change. For example, if in that situation later on, r is more dominant. Okay, for example, if you have cylindrical. Okay, for example, if you have cylindrical. Okay, let's say it's a full. Okay, a full cylindrical. Okay, you try to solve this situation equation. So what is the most dominant one that is change? Okay, so here, so the dominant one here is r, because you can have r here, you can have r here. But how about phi? Phi doesn't have really any dominant, because you can see it's just like 2 pi. Okay, and z is the same. Okay, so this is what means that we try to solve it considering only one variable. Okay, we put the focus to that one variable. And then separation of variable is if v is a function of more than one variable. Okay, so you can see in our syllabus, okay, we only focus on the A. We focus on direct integration when v is a function of one variable. Okay, the solution at this point is not unique, but is expressed in terms of unknown integration constant, which is to be determined. Okay, so what does it mean by this? Okay, because when later on, okay, you see like Laplacian operator, we have this, right? means we will have up to 2 times of integrations. Okay, when we try to integrate, okay, when we try to integrate, for example, let's say dx, okay, but we have okay, so the our answer will have like ax plus b plus c, okay, because we integrate one and we integrate another of times, okay, means we have 2 constant, okay. Then number 2, apply the boundary condition to determine a unique solution for V. Imposing the given boundary condition make the solution unique, okay. So you see, this is the definition of the unique theorem, okay. Okay, having obtained the V, we will find the E using potential gradient of V, or D from D equals to epsilon E, and J from J equals to sigma E. What is J? This is current density, okay, don't mistaken with current, it's different. If required, we will need to find the charge Q induced on a conductor using Q equals to rho S ds, where rho S is dN and dN, okay, where rho S is equals to dN, okay, or okay, this one will become scalar, okay. dN is the component of D, component of vector D normal to the conductor. If necessary, the capacitance of 2 conductors can be found using C equals to QV, or the resistance of J can be found by using Ri, where I equals to J ds. As you can see, right, we have several equation related to capacitance, several equation related to R. This is just a general representation. You can see C can be various. If you have capacitance for the coaxial cable, capacitance for this, which I already shown in the previous lecture, and R, if you want to solve during field approach, using field approach, we have a lot of possibility to obtain R using field approach, okay. So this one is you can read, okay. Now without okay, I will explain the example first before we go to the equation for the practice, okay. There are a lot of practice here, so I just go to the simplest one, so for your basic understanding, and hopefully you guys will try out yourself, and inshallah you can do it, okay. Okay, so if you can see, some of it I already covered in advance, okay, even though they are sharing from the same chapter, okay, like 249 I have covered, okay, for the tutorial 5 solutions, okay. So I have covered until 253, okay. So you can feel free to watch to see, okay. So some things that I have covered already before, okay. So you see, this is the field approach, okay. This is one of the equation for R, okay. So we have, and then for capacitor we can have parallel plate, we can have coaxial connect capacitors, okay. We can have many others, and then you can see like this. Okay, I just want to go through like this, okay. You can see we can have this kind of given questions, okay. So where you have is the phi is not 2 pi. What is the phi here? The phi, what is the phi here? If you guys can answer to me, it's actually from 0 until 5 over 2, okay. How about the t? T is nothing interesting, it's still t. And AB, you have a difference of A and B for the radius, okay. So no shortcut for EMT, do exercise more, okay. Okay, now we go for this first. Okay, I just explained before we do the exercise. Okay, now current carrying components in high voltage power equipment can be cooled, okay, to carry away the heat caused by ohmic loss. Okay, current carrying component, so it means that it have current. Okay, you need to extract the important information. Can be cooled to carry away the heat caused by ohmic loss. A mean of pumping is based on the force transmitted to the cooling fluid by charges in an electric field. So you can see there is another important information: force, charge, electric field. Okay, electro-hydrodynamic pumping is modeled in figure 6.1. Okay, the region between electrodes contain a uniform charge rho naught. Okay, why is used rho naught? Rho naught means at times, most probably rho naught is at time 0. That is the initial condition. Okay, which is generated at the left electrode and collected at the right electrode. Okay, which is generated at the left electrode here, rho naught, which is generated at the left electrode and collected at the right electrode. Okay, calculated the pressure the pump if rho naught, okay, equals to 25 millicoulomb per meter cube and V naught equals to 22 kilovolt. Okay, sometimes they didn't mention what is the nature of that charge density. It can be volume, it can be surface, or it can be line, right? But it's simple. The way to know is the units. If you have m power of 3, means it is a volume charge density. Okay, so by the equations you can see that rho naught having a value. When rho naught having volume means this is not equals to 0. What is our equation that need to be implemented? Yes, correct, it's a Poisson equation, because our rho v is not equal to 0. Okay, then you can see we can straight use this. Okay, Laplacian operator of v, negative rho v naught, rho v over e. The boundary condition you can see at v equals to z equals to 0. Okay, v naught here, and vz equals to d equals to 0. Okay, shows that v depends only on z. There is no radius or phi dependence. Okay, so actually to further to explain this situation, okay, so it have y, x, z. Okay, so our length is from 0 until d. Okay, and then there it shows that this is positive v naught and this is your 0v. Okay, and then this is your area S. Okay, the surface area. Okay, just like what I explained just now, one variable only. Okay, now we want to see the dependence or dominance. Okay, you can see why. Okay, using direct integration where v is a function of one variable, we try to put which one is the dominant. So if you see these situations, okay, if you see this equation, the dominance one is what? The dominance one is z, correct? Okay, so because rho v naught is not equivalent to 0, so you use Poisson. Okay, straight away. Okay, straight away you just use this rho v over epsilon. Okay, and after that, this one is a, and this one you need to mention which coordinate you need to use. If this is cylindrical, for sure you have r. What is the other variable? Phi and z. Okay, but because we can see this is changes more to z, okay, z is the dominant one, so you can just like this. Then you have negative rho v over your epsilon. Okay, so when you integrate this way, I told you when you guys integrate, you will have more constant because you need to integrate twice. Okay, because it's double integration. When you integrate once, you will have, okay, when you integrate once, okay, you integrate first integration, you will have negative rho v over epsilon in the function of z plus a. Okay, then you integrate another time, then you have negative rho v over epsilon, and this z will become what? Will become power square, and you have another 2, and this one will having az n plus b. So now you have two constant here. Okay, then with what is the question, what they want to calculate the pressure. Okay, so you can see this one you need to solve. Okay, how you need to solve? Okay, you see when z is 0, what do you have? When z is 0, you have v equals to what? V naught, right? So you solve this, and then when z equals to d here, your v will become 0. Okay, as what you understand in mathematics, additional mathematics, is if you want to solve two unknowns, you need to have two equations. So two unknowns, two equations. So most you already get the what is the b, what is the a, and what is the b. Okay, solving that, you obtain, okay, you obtain the v, okay, and you obtain the v with the value of a and b defined. Okay, because you already determined that, and then from there you obtain the e. Okay, obtain the e, electric field, from the potential gradients. Okay, and the net force. Okay, the net force. Okay, let me see for a while. Okay, this one is from, let me find the equation. Okay, I know the equation, but I need to find the pages for you to refer. Okay, wait for a while, because the net force it does not just simply come there. Okay, you have the, it have been introduced before. Okay, I need to find for you guys to refer to. Okay, okay, so you guys can refer. Okay, sorry, you guys can refer because it is I think it's already maybe covered or not covered, I'm not sure. Okay, okay, to want to know more about these equations, okay, you can see, right, like I teach you guys, if it's integration, it is a continuous surface, but if we have summation, it is a point, means it's not a continuous, maybe point by point. Okay, so this question, if you want to know more, please refer to page 184, which is force on electrode with charge E. Okay, you can see negative E. Okay, I think this is the equations. Where else? Because for me, I remember there is equation, but because you know, we don't specifically, we are not robot to specifically remember each and every page. Okay, Okay, so rho v is actually your charge density, right? Okay, F equals to integration of rho v e. Okay, so you get the force. Okay, you get the force having value of rho naught s v naught az. What is s? S is actually your surface area. Okay, in this case your surface area is this. Okay, so what is this surface area? Pi r square. Am I correct? Okay, so the force per unit area or pressure. Okay, so you see sometimes you need to remember the basic knowledge from your secondary school. Okay, what is the pressure? Okay, pressure is force over unit area. Okay, pressure equals to force over unit area. This one you have, this one you have, this one you can solve for force. Okay, and of course because it's force per unit area, the equation the unit is n, this is area, so meter square. Okay, so I'm explaining the example, hopefully you guys understand. If not, so sorry, I cannot so sorry if I don't explain clear enough. Okay, I try my best, inshallah. If you guys try the exercise and handout, okay, so that you master this subject, this exercise even more. Okay, you can see there's a lot of things covered in the slide. Okay, of 18 pages. Okay, so you guys can have some time to read that, but most basically I already covered that. Okay, so now we go for this. Okay, we go to practice 6.1. okay, we go to practice 6.1. so we try to read first and understand the situation, because important thing is you understand, even though it might take some time, but because understand is the most important thing. If you're able to understand, then you might able to solve it correctly. Okay, so let me see the question is the situation first. Okay, in a one-dimensional device, okay, one-dimensional, the charge density is given to rho v equals to rho naught x over a. You see, if it's having value directly Poisson. If e equals to 0 and x equals to 0 and v equals to 0 and x equals to 0, find your v, find your e. Okay, this is the situation. Okay, and this is the step. Okay, so let me try to do it slowly. Okay, so this is page number 1. So page number 3. So what they told us, in one-dimensional device, the charge is given. We extract the information first. This is important. So practice 6.1. Okay. Oh, wait for a while. Let me sit. Sitting for 40 minutes already. I'm tired. So I hope the video is clear. Okay. So okay. So we are given the rho v, okay, which is rho naught x over a. Okay, and then what is another given? And then it says that e, vector e, is 0 and x equals to 0, and v is 0 and x equals to a. Then the question asks, find v and e. Okay, so when we saw this Poisson, directly we use the Poisson equation. Okay, okay, this is the general equation. We need to adapt to our situation. Okay, So this is rho v, okay, negative rho naught x over a, okay. Now this one is double integration, a double differentiation. So you can see what is the dominant here, okay. What is the dominant variable? Clearly, if this is x, y, z, clearly it's a Cartesian, right? But like I told you guys, direct integration when v is function of one variable, okay. Our syllabus is on one variable, so we need to see what is the dominant. Of course, it just mention x, so it's made easier. So clearly is in terms of x only, okay. Then negative rho x over a, okay. So when you solve for double integral of this, you will come across that negative rho naught x a will having what? Will having this one x, you have initial x already. So when you have integral is actually what? Is actually x cubed over 6, am I correct? Okay. And don't forget there is epsilon, okay. So this is the one, the rho v. Okay, this is your rho v, and don't forget you need to put, okay, let me put different colors so you guys can see that is very important, easily to leave out, okay. So for me it's night time, so so it's easy for me to lose focus, okay. Don't worry, it's okay, as long as I want you guys to the best for everyone, okay. So my night sleep is disturbed is not important compared to your future, okay. So you see there is epsilon, right? Okay. Then you remember when we have double integration, so for sure we will have two constant, right? The first stage of constant you will have a, right? And then you integrate again, then you will have this one and you have this one, okay. Am I correct? So this one you don't need to put because some is included inside, okay. Now we have this our v. Then you see from the equation, okay, we have this already v, okay, but the equation is giving us e. It doesn't giving only all the v's to nicely include inside, okay. So that's why you can see from the guidelines, okay. Okay, always refer to the books. 3, having obtained v, find e using this, okay. So we can use this, no problem, okay. So we introduce, so we're using this, the potential gradients of v, okay. We try to solve this, okay. So v so e is actually the integration of this another guy, okay. We integrate and we differentiate with respect to what? Yes, x, because x is our dominant now. We want to integrate this guy, okay, and we want to differentiate this guy. So negative so negative become negative become positive, okay. So rho naught x cubed over a6, okay. And of course epsilon, right? And then plus ax plus b, okay. So what is the results of this e that you have? So solving that, you will have what? This one certainly is 0, right? So this one you left with a, okay. So because this is vector, so you need to have your answer in vector. Since this is all about x, so you need to have unit vector x. Okay, so solving this, you will have, okay, two epsilon what, a, am I correct? Okay, I need to look again for the answer. Okay, 2 epsilon a, because you see, I thought it's 9 because at night time, you know, my eye is not really good. So, okay, so minus minus of a, okay, remember this one is minus 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 minus, that's why it is plus. So if it is plus, this one should be minus. Okay, I'm sorry for that. Okay, because this one is minus minus, this one is positive, but remember is this one is negative, this one is positive, right? So sorry for that, for some errors. Okay, then after that you have your a already. Okay, then in the x you need vector, you need the vector in the direction of x. Okay, then or you can only use this condition. Okay, now what they say to us, okay, if e is 0, x is equal to 0. So we try to insert this situation. Okay, so e is 0, e is 0 when x is 0. Okay, so we don't care about the a's because this is already 0. Then minus a. So then you get what the value of a? Your value of a is 0. Okay, and the next one, they tell v equals to 0 and x is equals to a. So solving that, v okay, since you know this is 0, right? So you just update first your equation that you have. So this is 0, right? So now you only left this. So next is when v is 0, x equals to a. So when v equals 0, 0, x equals to a. So you can see this one, you can cancel out, you have a square, right? So what is your b then? Your b is actually this one rearranged, then you have rho a over 6 epsilon. Okay, so what is the complete equation that you have? Sorry, the light is, I don't know why it's like this, it's blinking. Maybe it's telling Raimi, please, it's night time, you should be sleeping, because now it's 2 to 5 a.m. Okay, it's okay. I might be a bit headache tomorrow, but it's okay. Okay, so what else? Where else I go? Okay, so we have this b now. So we have v equals to negative rho naught of x cubed over a 6 epsilon. Okay, this one a bit messy, is okay, we can do it later on, simplification. The important thing is for you to get the answer first. Okay, now you have your b, right? Okay, now you can do the rearrange. Okay, rearrange, because of the terrible way it doesn't look nice. Okay, it doesn't look nice, so we can we can take out things that is common. Okay, thing that is common here is rho naught. Okay, okay, so what is the common is actually rho naught over what, 6 epsilon, right? We can take it out. Okay, and also what else? We can take it. Yes, we can take a out. Okay, we can take a out. What else? Okay, I think that's all. Okay, so now this is minus and this is positive. So now since we take it at all, so we have x cubed plus 1 plus a3. Why a3? a3 with a, later on it become a square again. So to make it look nicer, okay, to make it more nicer, rearrange. Okay, so what is the question? So the question is asking for v, so now we have our v. Okay, now the question, then it says another one they want us to find is the e. Okay, also simple. Once you have your what is your e? Your e is already, we already have our e, right? Okay, this is our e, more or less. Okay, so your e is rho naught of x squared over 2 epsilon a in the direction of what? X. Okay, so alhamdulillah we finish. Okay, this is for basic, and I hope you guys will try out. Okay, please read. Okay, no shortcut, please read and try to do, because like this, right, you have the answer. I think I'm not sure, am I already covered this last time? You see, I think I already covered. Okay, I already covered this. Okay, so alhamdulillah we have finished about this Laplacians and Poisson. Okay, so see you in the next lecture. Okay, see, I let me zoom out so you can see the whole solutions. Okay, okay, sorry for I'm not sure. Okay, okay, thank you very much. Assalamualaikum and see you soon.